Okay, we're live.
Welcome, everybody. My name is Sepp Hochreiter. I'm a fellow of the ELLIS program and an ELLIS board member. First of all, in the name of all board members, I want to thank you a lot for your support for ELLIS. We already achieved a lot. The programs are running and workshops already in progress. You are participating in one. The PhD exchanges are already set up. Perhaps some hints concerning ELLIS. If you want to become a supporter of ELLIS, please go to the ELLIS site. It is ellis.eu. Go to people, there go to supporters, and there's a button where you can sign up as a supporter. We are happy to have many supporters. If you want to become a member, also go to the ELLIS site, ellis.eu. Go to people, and there's a sub-menu, and that's members. There you get instructions how you become a member. And perhaps as a company, you even want to become an ELLIS sponsor. Again, go to the ELLIS site, go to the subtopic sponsorship, and there's information how to become a sponsor and how get your company involved into the ELLIS initiative. Perhaps some news from ELLIS. The ELLIS fellowship program opened a new call. There's a call for proposals. Deadline is the 1st of June. This call is open now, and we are happy to see many proposals for ELLIS programs, for ELLIS fellowship programs. Now I'm coming to this event. That's the first, as a third follow-up workshop called ELLIS Against COVID, where we present new research, new tasks, new ideas, or even new data set, where ELLIS members, machine learning researchers tackle the COVID crisis by helping the health guys, helping medicine, analyzing the data. There was already a workshop. The first workshop was on 1st of April. It's on YouTube. Check out again, ellis.org. There's a button, ELLIS Against COVID. You can still see everything on YouTube. Also, the second workshop, it was on 15th of April. It's on YouTube, ellis.org, button ELLIS Against COVID, and you can watch everything what was presented at the previous workshops. Let me start with the program of today. We have 3 sessions. The organizer is Michaela van Naschar, Gunnar Retsch, Bernhard Schöllkopf, and Oliver Stegle. We are one team, and we're alternating with another team organizing these workshops. I'm chairing the first session. It's epidemiology and modeling. And I make it short. Our first speaker, we only have talks about 10 minutes. We have 3 talks in the first session, about 10 minutes. And afterwards, there's a question discussion session with 15 minutes. The questions can be entered in a forum, which should be also online. You can enter your questions and I will check them and I will ask the speakers for the question. The questions will be after the third speaker and in a block. Then I'm very happy to welcome our first big name. It's Peter Grünwald, and I give you the floor already. Peter, welcome, take over.
Okay, thank you, Sepp, for the nice introduction. Let me put my slides. Let me share the screen just a moment. Oops. Okay, so I'm heading the machine learning group of the CWI. That's the Dutch National Center for Mathematics and Computer Science. It's a bit comparable to Max Planck Institute or INRIA in France. Of course, we also wanted to do something when the Corona crisis came. So with part of our group, we are now assisting the University Medical Center, UMC of Utrecht, with some randomized clinical trials that are directly related to Corona. And this is jointly with my PhD students, Rosanne Turner and Judith Ter Schuren, and a former postdoc, Alexander Lee. So what is this about? Well, okay. There is this vaccination against tuberculosis. It's called the BCG vaccination. It's actually a very old medication. And it's known that it gives a generic boost to the immune system. And in many countries in the world, of course, hospital workers are now needed basically day and night, especially in the Netherlands. If you compare that, for example, to Germany, we have much smaller intensive care departments. So people are really doing crazy shifts. So we need all the hands we can get at the hospital beds. And the idea is that because this BCG vaccine is known to give a generic boost to the immune system, and it's also known to be harmless, it has no side effects, at least no negative side effects as far as we know. The idea came up to that maybe you want to vaccinate health workers with the BCG vaccine so that they don't get ill as much as they normally do while they are all needed. And so there would be then 2 things to look at. Do they get generally less ill, and also do they not get Corona? So that is the first trial we are involved in. What is interesting is normally if you want to do a randomized clinical trial, you need at least half a year to get all the permissions from the medical ethical committees. In this case, they got it in 3 days and they've already started. And the second trial, which will start shortly, also these vaccinations will be given to elderly people with the idea that maybe we can bridge the period between now and when there's a vaccine against Corona. So in the meantime, maybe if we can boost the immune system, the probability that they get ill of Corona is smaller. So the first trial, I'll concentrate on that one. It's already started. It's a classical randomized clinical trial. So you get 750 hospital workers, which get the vaccination, and 750 get also a vaccination, but it's a placebo. They are spread over 9 hospitals. The primary endpoint, so endpoint doesn't mean end of study, it means like the goal in randomized clinical trials, is the number of days absent due to sickness. So they want to check if in the group which gets the real vaccination, people are less often sick. But then there's also an alternative endpoint, which is not what they study in the first place, but it might become important later on. And that is a more classical thing that's often done in medical trials, which is it's time to event. So it's like you measure like how much time is there between a vaccination and a first day that people get ill, if they get ill at all. Now, where do we come in? As CWI, and of course, we're not medical statisticians, but there's this issue, which is a generic issue with randomized trials and with hypothesis testing, but here it gets especially urgent, which is that classical randomized clinical trials, they're basically based on p-values and classical hypothesis tests. And as is well known, they are very inflexible to things like optional stopping and optional continuation. So optional stopping means that if it doesn't work at all, then let's say everything is futile, or if it seems to work really very well, you want to stop early, which in this case is really important, because if we really have a lot of evidence that this vaccination works, we should stop. It would be unethical to give people placebos. We should actually start injecting everybody with the TBC vaccination. Another thing that can happen is that after these 1,500 data points have been gathered, you have some evidence that it works, but it might not be strong enough. Like you might not be statistically significant, or the effect, the confidence interval around the effect might be too large. And then you might want to look at, let's say, let's take 500 more and let's combine the results. Both of these things are essentially almost impossible with classical hypothesis tests. People do it anyway, and that's one of the reasons why we have this replicability crisis in science. People use p-values. When they do optional continuation, they add another 300 data points, and then they use a p-value for this new, bigger number of data points as if it had been decided in advance. If you do that, then your evidence that the medication works gets inflated by quite a lot. So we need methods which can handle with this in a generic way. You get type 1 error guarantees, statistical guarantees that you probably make the right decision if you decide whether or not the vaccination really works. And so this is where CWI comes in. We have actually worked on this very hard for the last 2 years. And we have found generic testing methods for which can basically always handle optional stopping and optional continuation. And that's especially in cases like this corona case, when time is of the essence, it's really important that you can stop early or that you can continue. It's also important that you can combine results in a nice way, which doesn't mess up your statistical error guarantees. And that's becoming important here as well, because we started 3 weeks ago, but by now there are 3 other tests of exactly the same question have started around the world. There's a very big one in Australia. Yeah, one thing I should add here is that in many studies these days, it's of course well known that there are many issues with p-values and hypothesis testing. So also in the medical world, people often have stopped using p-values and tests. Instead, they use confidence intervals. But confidence intervals have exactly the same issue. And we're also working not just on tests, which can deal with optional stopping and optional continuation, but also confidence intervals. So what we have that came out in a paper last year is a generic method to create tests which can do optional continuation. So basically, you give me a null hypothesis and an alternative, like in a classical testing situation, and I have an algorithm which basically creates for you a test which can handle optional continuation. So it means that type 1 error guarantees the probability of making a wrong decision if the medication doesn't work and you still decide it works. That probability remains below 5%, even if you do optional continuation. Now, in general, this recipe we found for doing that can be computationally problematic, but we looked at several specific cases, and there actually we found fast algorithms for it. So we now have an R package. I'll give you the link at the end of the talk, where we have a safe t-test and a safe 2x2 test. Of course, these are super simple tests. They're the simplest tests around. They're 100 years old, but we have to start somewhere. And so these were the first ones we tried to tackle. So just one technical slide. How does this, what we call safe testing, work? This testing which can deal with optional continuation. The abstract definition of a p-value is that it's some random variable, not a value, but a random variable, some function of the data. And the probability that it gets smaller than alpha is smaller than alpha. So the probability that you see a p-value smaller than 0.05 is smaller than 0.05. That's the standard definition of a p-value. And instead we have something we call an s-value. Now, what's the difference? There are some caveats here because I'm showing you only a special case of the s-value. There's an existential quantifier on the sample size. So the p-value has to be defined. If you want to define a p-value, you have to know the sample size in advance, it's n. And an s-value, you don't need to know the sample size. And you get a guarantee, which basically says the probability that at some sample size, you will go below alpha is below alpha. So this means that you can stop essentially at any time you want. And the probability that if you see something smaller than alpha, but the null hypothesis is true, then this will probably never happen. So it also will not happen at the particular time you like to stop. Well, this is related to something called always valid p-values, but the s-values have some other properties. And one very nice property is that if you have several tests, you can multiply the corresponding s-values and you still get something meaningful. With p-values, that's impossible because if you multiply p-values, they always get smaller than 1. And this means that you automatically get more evidence that the medication works, which cannot be right. So with these s-values, you can multiply them, and that's very helpful. So on the package, you can play around with this. Here's an example of things you can do with the package where you can see what happens if you do early stopping. So here we stop as soon as we get a significant result. And then we see that if we compare this to standard testing, we need a little bit more data. If we stop at a fixed time, we need more data than with standard testing. But if we allow to stop early, on average, we need about the same data or even less. Now, what are the challenges of using this in the medical context? Well, of course, we bumped into this test, which was actually already almost underway. And their basic model is just way too complicated to design a computationally feasible test with optional stopping. I mean, we would need months for that, basically. So that we could not do. But then there's the secondary endpoint they look at, which is not the number of days that somebody is ill, but the time to event, which is also what is looked at, for example, in the Australian randomized trial. So they look at how many days after vaccination does it take before somebody gets ill. And so what we did there is we made a safe test for that, which was very challenging because this is survival analysis. It's a field which we knew nothing about and which has all these things like censoring, people might drop out of the study. So we managed to make a test for that, a safe version, which can do optional stopping of the classical log rank test within 2 weeks. So it was very hard work. And we now also have a safe version of the Cox proportional hazard regression model, which is kind of the bread and butter of these survival analysis methods. So final slide, a final challenge is that we are basically trying to convince the people in Utrecht to use a method which needs slightly... Sorry, this is the last slide. So we are trying to convince them to use a method where you need a little bit more data to get the same power, or with the same data you get a bit less power. But you get a lot of flexibility back for that. And it seems that we have convinced the main statistician, but of course we also need to convince the medical people. So it's still not completely clear whether it's actually going to be used in their trial, but we have good hopes that it will be used. And we have helped them with their design, and we have helped them in general to kind of improve the statistics of their trial. So that was my talk. Thanks again for giving the opportunity.
Thank you, Peter. Great talk on statistics. I go ahead because we're a little bit behind the schedule. The next speaker, which was announced, is Marco Gori. He could not make it, but we have a perfect substitute. It's Alessandro Betti. He's from the Siena Artificial Intelligence Lab. Alessandro, please.
I'll try to share. Can you see the slide correctly?
Yeah. You see it?
Okay, so thank you. I'm Alessandro Betti, from a postdoc from CELAB at the University of Siena. And in the next few minutes, I would like to talk about an activity that we are conducting together with Marco Gori, Enrico Meloni, and Andrea Zuccarini about learning the parameters of a dynamic SIR model. Before we start, just a warning. I want to warn you that the content of this presentation is based on a very preliminary research, and this comment is particularly relevant for the experimental result that I will show at the end of the talk. So first of all, I would like to revise the basic SIR model just to fix the notation. So in the classical SIR model, we assume that the population, that we have a constant population divided into three groups that are the susceptible, the infectious, and the removed. And I will call X of t the number of susceptible at time t, Y of t the number of infectious at time t, and Z of t the number of removed at time t. And of course, since we have a constant population, the sum of all these three variables should be constant for any time. In the simplest formulation, SIR model is defined through a system of three ordinary differential equations, which basically tells how each of the variables changes over time. And once you give initial conditions, the dynamic of the system is completely specified by the values of beta and of gamma, which are the infection rate and removal rate. And it's also convenient to define this reproduction number, which is in this case R naught, is the ratio between, is just a ratio between beta and gamma. So in what follows, we will consider a slight generalization of this epidemiological model, which is known as dynamic SIR, where we assume that the infection rate and removal rate can have temporal variation. So we allow for extra flexibility to model changes in the way in which the infection grows. So the problem that we try to tackle, as I anticipated, is the problem of learning this function beta of t and gamma of t together with a fatality rate delta using supervision only on the number of deceased. Once we assume that the estimate for the number of deceased can, for example, in its simplest formulation, be expressed in terms of the solution of the SIR model as a fraction of the removed. So if we call W of t the number of deceased at a certain time, then we assume that we can express this number in terms of Z of t. And we decided to model, to use only supervision from that, because as far as we understand, but this of course is debatable, this is one of the measurements, of the simplest measurement that we can get, that compares to the other, for example, the number of infections suffer from probably a smaller error. So this is the general statement of the problem. Now let me be a little bit more precise on what we try to do. So we try to formulate learning as the minimization of some quantity that can be built as follows. So suppose you fixed a certain values of this function. So you give some function, beta, gamma, and delta, that from now on I will concisely refers to as u. And once you have fixed u and you have given some initial condition, then you can solve the SIR and get an estimate for w that of course is a function of time that depends on the choice that you have done on the on u. And then on the other hand, you have your supervision, your data that are indicated with w hat of t. And then what you can do is you can build this index, this functional as f of u, which is the sum, the integral over time of a loss, which is a square loss that indicates the difference between the estimated values of the debts and the data. And then we can formulate the learning problem, can state the learning problem by saying that we want to find the parameters that minimize this functional. And of course, this is in its general formulation in calculus of variation is as a control problem on the variable u. And we have decided to tackle this problem using a gradient flow on f. So we start from a guess u naught of t, an initial condition u naught of t, and then for every t we slightly adjust at every step this initial condition to get the solution of the problem. So now, as I said, I will try to show you some preliminary experimental results, and as I warn you, these are rather there is much room for improvement, but I think that they will as well give you much more intuition about what we are trying to do. So we performed an experiment using data from various regions, Italian regions, and here I've reported the result for Lombardia. So you see in the left side of the screen, in the upper part, there is the temporal dynamics of the parameters that we consider. There are beta, gamma, and delta. You can see that here we have chosen to have a constant delta. So delta is chosen to be a constant function whose value, however, is learned, while beta and gamma are developed as true function of time. In the lower part of the slide, you can see the corresponding value of the R naught relative to these values of beta and gamma. And looking at the magenta line, you can appreciate where these values go below 1. While on the right part of the slide, you can see the dynamics of the SIR model, which is in the general behavior follows the classical SIR model, but is, as you can see, slightly distorted from the fact that you have indeed varying coefficients. Okay, so these instead are the result on the fitting of the data. So on the left side, you can see the fitting that we are actually performing on the debts. And you can see that you have the red dots are the data. The one which are on the blue line are the dots that are actually have been used to perform the fitting. While the other data, the one over the yellow line are some data that we kept aside to evaluate our prediction. And you can see that at the beginning prediction is rather accurate, but then you have an underestimate of the deaths. And while on the right side, you can see the our estimate for the infectious that is plotted against together with the real data that we collected from the official measurements. And you can see here that there is this strange behavior at the end where our prediction go below the actual data, which is rather suspicious in this case. So yes, this is pretty much everything I wanted to say. I'll thank you very much for your listening and your attention, and for having given me the opportunity to talk to you. Thank you.
Thank you, Alessandro. Great talk. I go immediately ahead. We are behind the schedule. we have Johannes Zierenberg from the Max Planck Institute for Dynamics and Self-Organization from Göttingen with us. Johannes, please.
Thank you very much. So thank you for the introduction, and I would also like to thank for the opportunity to present our work in this format, which is very new and exciting for me. This is such an online workshop. So in fact, I'm sitting right now in Spain, and so otherwise this would have been costing a lot of carbon emissions. So I really like this idea of putting this online together. And before I start, let me introduce you briefly to the team that did most of the work. So can you see my mouse?
Yes.
Yes.
Oh, perfect. So this is Jonas Dening. So then you can have some idea about the faces. This is me. This is my face. This is Paul Spitzner. Here we have Michael Bibral, Joao Pinheiro Neto, Michael Wilczek, and Viola Priesemann. So we are the core team of what happened in the past weeks, where we tried to infer the spreading rates of the COVID-19 outbreak in Germany. So we focused on Germany and the whole German to start with. And what we actually wanted to do is we wanted to describe the spread of the outbreak in Germany by a simple mathematical model. And I'll tell you in a second why. And then we wanted to infer the parameters of this mathematical model. And in particular, you wanted to know the uncertainty of these parameters. And then we wanted to use them to forecast future scenarios where we could look at different things that could have happened, and particularly also to propagate the parameter uncertainty. And the parameter the mathematical model we chose is similar to the previous talk, the SIR model. Let me briefly introduce the dynamics. So let's say in Germany we have a couple of people. These are the black people here, and there's an infected person, and that can spread the disease. And at some point, this person can get recovered, but the disease is continuing to spread. So we just put all these people into different compartments, and we call them the compartment of susceptible people, the compartment of infected, and the compartment of recovered people. And then every person can go from one compartment to the other. So for example, an infected person can spread the disease with a rate lambda to some susceptible person, and this becomes infected. And any infected person can recover at a certain rate nu. And we can express this SIR in these discrete differential equations. And it's very similar to what we saw before, just a little bit different notation. So we have the per individual connection spreading rate, so to say, introduced here. So we get an extra term 1/n here. So we see that the number of susceptible people changes over time according to this fraction that depends on the current number of infected and susceptible people, and vice versa. The pool of infected people increases by this amount, but decreases governed by the recovery rate. And for a large pool of susceptible people, the dynamics is essentially controlled by the growth rate, because this factor here is just 1. So the growth rate, the effective growth rate, is just the difference between this spreading rate and the recovery rate. And this is then essentially multiplied to the path state. So why did we want to have a simple model? Because we wanted to do Bayesian inference. And the main idea here is that we wanted to estimate the probability of seeing model parameters given the observed data that we have, but also including our prior knowledge about what we know about the disease. So the main idea is that we want to sample the posterior distribution using Markov chain Monte Carlo simulations, and where we wanted to see the probability of having certain parameters describing the data, which is proportional to some likelihood that we formulated, where we see the probability that we observe the data for some parameters. This is essentially driven by our dynamical model, and then combined with the prior of previous parameters of the parameters. And let me just illustrate this, how this works, on 2 examples. So for example, the recovery rate, we have a rough idea that that people can be infected for about 8 days. That was kind of going around in media and in the literature. So the recovery rate is fairly constrained to be 0.12 in terms of days. So we formulated a narrow prior. This is a log normal distribution. This is the gray line here for this recovery rate. And then we did our sampling, and we see that the posterior that comes out is fairly consistent with this prior. So the data didn't constrain this. And on the other hand, for example, we also fitted the scale, the width of this likelihood function. I won't go into detail, but since we had no idea about that, we chose a very flat prior and essentially let the data constrain this parameter. And the last thing that we introduced is because we were also interested in a dynamical model is we introduced change points, but we didn't do that continuously, but we really said, okay, let's say that governmental interventions really act as change points in the spreading rate. So we have some spreading rate lambda that's constant over time up to some intervention point, and then we have some sort of a linear crossover to some other plateau of a new spreading rate. And this is just a case where we have three different scenarios. Nothing changes, there's a slight change, or there's a strong change in the spreading rate. And the interventions that we considered are the three main interventions that happened in Germany. The one is on was on March 9th. We had the cancellation of large events with more than 1,000 participants, or around March 9th. Then we had March 16th, where the schools were closed, child care centers as well, and majority of stores. And then there was March 23rd, where we had the contact ban introduced and closing of all non-essential stores. And without going into too much detail on how this whole machinery works, I can just show you what we got from this. So what we wanted to do is to quantify the governmental interventions. And this is a huge figure, but I'm going to go through this slowly. So let's focus on this part first. So what we had is data. These are the blue dots here. This is the new daily cases confirmed in Germany. And this is typically what we see in the media. It's the total confirmed cases in Germany, which is growing, but this kind of is variable over time, right? And what we did now is that we let our model generate different trajectories and looked at the likelihood and particularly also combined with prior to see which parameters describe this well. And then we get distributions for these parameters. One particular thing that I want to focus on is that in order to do this properly, we had to introduce a reporting delay between the real effect of the disease in the community, and the time when it's actually recorded. So this the reporting delay, which is has three contributions. It's on the one hand side, the biological incubation period. Then we have a delay from first symptoms to symptoms motivating a test, and a delay before testing results come in. So this gets inferred by our model to be roughly 9.5 days, and this is not completely similar to what we put in as a prior. So this is constrained by the data, and it's consistent with what one would expect from the literature to actually observe in Germany. And then what we actually got out is this time-dependent spreading rate, and with these three interventions, and in particular, because this is the model where we put all three interventions in, we can see that March 9th, so the cancellations of large events, they were roughly also fitted by our model around March 8th. And they just reduced the spreading rate to something like 0.25, which is still above the recovery rate. So we would still expect an increase in new cases, which kind of would have gone up here. Then we had the second intervention point. This is here on March 16th, where we had the closing of schools, and we see that this lowered the spreading rate to 0.16, which is still above the recovery rate. So we are right here now, this plateau. And this would have been this case here, where we would still observe an increase of cases. And only the last intervention, where we had introduced the contact ban and the closing of all non-essential stores, that really reduced the spreading rate, presumably below the recovery rate, so that we can actually now see clear decay in new cases over time. And then we can use this model and forecast what happens in the future, in this case, under the assumption that nothing changes. And also we compared to different realizations of models like 1, 0, 2 or 3 change points, and we found that this currently is the model that best describes the data. And then we can do forecast scenarios. So for example, we can think about what happens during Easter, and we know a lot of people did visit their families, even though they might have not, were maybe not supposed to. So we would maybe expect that there's a slight increase in the growth rate again, but it's probably just a bump. And then we can think about what happens now when we relax our interventions or restrictions. And there's actually 2 scenarios. One is stays the same or it increases slightly. And we can see this also now or we can use our model where we now, disclaimer, so we now have a new model here, which also incorporates the fluctuations over weeks in reporting, because this is actually also an important effect. And we can see that if everything stays fairly well behaved, we still are on the track of decaying new cases. But if now things just go above 0 in terms of this effective growth, we kind of just get back into the exponential growing phase. So this kind of can be used in order to be aware of how to deal with future potential interventions if we really want to get down to a level where we really want to track individual cases, for which we would say that we would kind of get below 1,000 new cases per day, or even fairly well below that. So as a summary, we started with inference of model parameters on the level of Germany in order to propagate the parameter uncertainty into future scenarios. We need to have a very simple model for this, because otherwise this whole Monte Carlo sampling would just explode in computational complexity. And the next steps that we are doing is now hierarchical inference on the level of federal states, together with a team from Alexander Ecker, in order to really boil this down to the different federal states, in order to get a bit more heterogeneity in the model, because right now we have this well-mixed assumption of SIR models on the global state of Germany. So we're curious to see what effects come in from there. And with that, I come to acknowledge this very nice work together the past 4 weeks with this team, the funding, which I forgot to mention in the beginning. And I would like to thank you for your attention.
Thank you, Johannes. We are on time, and therefore we have only time for a few questions. First question to Peter. Peter, can you give some details about how you helped in the experimental design of the RCT?
Yes, so can people hear me?
Yes.
Okay. So what we did was that, so basically these people are kind of working day and night as well. And so they're making these, if you do a randomized clinical trial, you always also have to make a statistical plan, and they had made that in a very short period. So we noted that for the, it was mostly for the second trial, we noted several strange things in their statistical design. So one thing was that they wanted to do a 2x2 test in the second trial, where they test for elderly, which is like, well, I don't remember the details, but that just seemed generally not a good idea, because you you have all these things related to survival analysis that people may drop out of the study or come in later. So we convinced them that for the second trial, they should do a time to event analysis. So things like that, basically.
Thank you. Then I have a question, time for another question to Alessandro. How do you handle a very non-exponential distribution of time to death? Because it appears bimodal. Some people die quickly and others after a couple of weeks.
Yes, thank you. Yes, this is indeed a crucial point. We first used the dynamic SIR model because of its simplicity, and we completely rely on the idea that the coefficients, the removal rate, for example, can to a certain extent absorb this kind of behavior. However, we are now trying to consider extension of the underlying model to incorporate these kinds of effects, for example, by using an equation that estimates the rate of change of deaths with some kind of convolution, explicit convolution. The crucial point is the fact that our method is to a certain extent quite independent of the underlying model. So the answer is that we started from this model, but then we are trying to generalize to new models, and also this is an opportunity for suggestion. If you can come up with meaningful ways to replace this SIR model, we would be welcome to hear from you. So thank you.
Thank you. My last question to Johannes. The disease has a consistent incubation period, 14 days with a 95 percentile. Why did you consider SIR and not SEIR?
That's a very good question. So indeed, I didn't have time, but we did do a lot of consistency checks. And in the course of that, we also did consider some realizations of SEIR-like models. So the main problem with SEIR models is that also that typically the crossover from the exposed to the infectious period is modeled with exponentially distributed times. So this is typically not the case what happens in diseases. So we instead use some convolution of log normal distributed incubation periods. It did not affect the main results very much. And the problem is that you get more parameters into the model so that the model fitting is just not getting much easier. So interestingly, the effects were very, very mild that came out. And importantly, the results on the spreading rates that we related to the governmental interventions were extremely consistent. So we put our paper on arXiv. There's these consistency checks there in the supplemental material. And we also have our code, by the way, on GitHub. So you can actually just play around with that and just extend it.
Thanks a lot, makes sense. There were more questions in the online form. We put it online. You can look up the questions. Our speakers will do it. Thanks to all speakers from the first session. And I will hand over to Gunnar. I think, Gunnar, you're heading the next session.
Actually, so Gunnar asked me to step in.
I hand over to Bernhard.
Okay, so yes, Bernhard Schlöckhoff to begin, and will be chairing the next session. And without further ado, so the next session is entitled Data, Privacy, and Machine Learning Challenges. And let's dive right in. The first talk will be given by Antti Honkala, a 10-minute talk on privacy-preserving contact statistics collection for COVID-19 epidemic management.
Okay, thanks, Bernhard. So I'm Antti Honkala from the Finnish Center for AI at the University of Helsinki, and I'm presenting our proposal for privacy-preserving collection of contact statistics to help modeling the epidemic and managing it. And this is joint work with Tejas Kulkarni from the Aalto University. So, as we know, the primary route of spreading for the coronavirus causing the COVID-19 disease is through long-term close contact. And to monitor the spread, many countries are developing mobile apps for contact tracing to be able to track potential routes of contact and therefore isolate people who have been exposed to it. Especially in the European context, privacy is an absolute requirement for these apps. And therefore, the typical mode of operation for the sort of better apps is that they don't use any location data because it provides too low utility, and it's also very bad for privacy, but rather are based on Bluetooth. So the devices are set to broadcast random identifiers, and then they record these corresponding identifiers broadcast by other nearby devices. And in order to preserve privacy, these identifiers change relatively frequently in a random manner. And then basically the only sharing of data is, so when a user is diagnosed positive, then the device will send a record of the identifiers for recent contacts that have been recorded. So this is all very good, but what we see here is an opportunity to collect more data. So these contact tracing apps collect data of close contacts in the population, and we believe it would be valuable to collect more statistical information of contact frequencies. So basically, how many people are different people in close contact with, say, over a day, as this would provide more data for epidemic modeling, as well as monitoring and planning these different interventions, as was discussed in the previous study. So obviously, we can monitor these by monitoring these deaths and sort of newly diagnosed infections, confirmed infections, but there are long delays and it's quite difficult. So in that sense, sort of more data might be really helpful. And while just this kind of statistical data, such as collecting the number of contacts, is not very sensitive, strong privacy protection is still necessary in order to get included in these apps. And also the collection should be opt-in. But we do believe that even in case of this opt-in data that might lead to a sort of lower percentage of people accepting this, this might still provide enough useful information for things like monitoring changes over time, even if we might not get sort of very accurate data for the population as a whole, or there might be some biases. So how to collect this kind of data in practice, and or sensitive data? Algorithms for this have been used by social scientists since 1960s, and the typical protocol would instruct the responders to answer such a potentially sensitive question by first flipping a coin in secret, and then, depending on the outcome of the coin, either responding truthfully or then flipping a second coin and answering whatever the second coin tells you. This is a very effective means of getting sort of personal protection for the response, so you get a plausible deniability. No matter what you respond, you can always say, well, it was just the coins. But still, if we collect the statistics from the whole population, then we can compensate for the noise that was added because we know exactly the process that was used to generate it. And therefore, we can get fairly accurate estimates of the true frequency of positive responses in the population. And effectively, what everyone sees here is like a probabilistic loss of privacy. So if you respond yes, then it's more likely that your true response was yes, but anyone can't still say that for sure. The theoretical framework that has been built upon this kind of ideas, introduced by Cynthia Dwork and colleagues in 2006, is of course differential privacy. The formal definition of differential privacy basically says that if we have two data sets that differ by data for a single individual, and we run some analysis on these data sets, then the probabilities of obtaining any specific outcome from these two analyses should not be too different. And clearly the randomized response mechanism shown previously is one example of this. The theoretical framework for differential privacy has many nice properties. First of all, we can show that it provides protection also against adversaries with side information, so it provides a very strong privacy guarantee. It degrades gracefully under repeated use. So if we are doing multiple queries, we can see how it will degrade the privacy, but it doesn't break down completely. And also it's invariant to post-processing. So if we have the result of a differentially private query, we can then run any algorithms we like on that. And it doesn't affect the privacy guarantee as long as we don't go back to the original data. So how to use it in this case? Our proposal would be to use a form of differential privacy called local differential privacy to collect population histogram of the number of contacts people have made as observed by these contact tracing apps. In local differential privacy, the data are anonymized so that the noise to guarantee privacy is added before the data leave the user device. So therefore, there is no there is no need for any trusted agent who would see the original data, but every user gets a guarantee of privacy. The rapidly changing identifiers used by these protocols have some difficulty because we can't reliably estimate the number of contacts over a day. But we believe that, for instance, collecting the largest number of contacts over any 30-minute period during the day should provide a reasonable proxy that's useful, at least for some modeling. In terms of technology, the very simple protocol doesn't provide a very high utility. So if for a given level of privacy, so it's possible to enhance the privacy guarantees by introducing what's called a secure shuffling. For instance, by submitting the data via a Tor network that makes it impossible to associate any reports with a given user. And this will significantly tighten the theoretical privacy guarantees. One caveat here is that if we are deploying this in a mode where we collect data repeatedly, say every day, then the theoretical privacy guarantees will degrade over time. This is partly mitigated by the fact that we're using fresh data for every report. so that the usual attack that would be that if you use the same mechanism to report the same data, then you could average out the noise. That doesn't apply, but still this is a potential weakness, and therefore some kind of ethical review of cost versus benefits is still needed. But overall, we get a sort of nice, although somewhat noisy, data that we can then fit to that we can then feed to a Bayesian model for denoising, and doing some kind of probabilistic modeling of responses over time to, for instance, model the effects of these interventions. So for some preliminary results, here's a simple simulation of how much error we would make in estimating the mean of a simulated distribution using this mechanism. And the data here comes from an underlying geometric distribution, and we show here values for different epsilons, which displays the level of privacy guarantee. Smaller is better. 1.1 is roughly this flip a coin. And D here is the number of bins used to collect the histogram. And we see here that we get reasonably good, pretty good estimates of the mean with reasonable level of privacy, assuming this population of approximately 1 million users. So to conclude, I think we all agree that it would be great to have more data to build our models and chart our way out of this epidemic or pandemic. And we believe that these daily contact statistics could provide a very nice direct measure of the most important spreading mechanism, and therefore enable more detailed models. And differential privacy is useful here for providing a means to collect such data under strong privacy guarantees for the users. And with that, I'd like to thank the organizers for the opportunity to present my work, and all of you for your attention. Thanks.
Thank you very much, Antti. Perfectly on time. But as usual, we move on with the next talk, and then we have the question discussion session at the end, so people can continue to submit questions also for Antti's talk. So we now move on to the talk of Thomas Hermans, who will tell us about the JEDI Grand Challenge.
Okay, good afternoon, everyone. I hope you can hear me properly. So I'm Thomas Hermans. I'm a professor in chemistry at the University of Strasbourg. Since the last couple of weeks, I'm the program manager for JEDI on a grand challenge to find a new therapeutic for the COVID virus. And please visit this website. So we're launching a global challenge where basically all teams can participate. And we want to tackle, we want to reach a number of moonshots. So moonshots are very challenging targets that we are trying to reach. So we're trying to, I will show you the details, but we're trying to model a number of components at a huge scale. And we try to get a very high hit rate. So we try to get a very high accuracy in the compounds that are predicted by cross-correlating the results of all the teams that are submitting to our competition. And we have experimental validation in place. So these compounds will be synthesized, they will be tested, and we will get hopefully high viral reduction. And also we have a track on finding new drug cocktails. So how does it work? So in stage 1, which is opening very soon, we encourage teams to screen over 1 billion compounds using 3 independent methods. And for that, we are also providing help and infrastructure. So on the first side, we are helping to identify the best protein targets. So for this, we are working with a number of partners. So we have the Corona Structural Task Force by Andrea Thorn, who's taking the X-ray diffraction structures and refining them to get the highest resolution 3D models. And people at Folding at Home, which is a crowdsourced initiative in the US, are doing energy minimizations on these structures. And also the simulation data and these targets will be all combined by MOLSI. which we will provide the details on our website. On the side of the chemical compound libraries, we're trying to get the biggest possible libraries. So there's, of course, the well-known Zinc-15 library, which has like 1.4 billion compounds. But we have also partnered with Merck, and they are opening up their own libraries, which we have already cross-ranked against Zinc. And we have identified 1 million new compounds that have not been in there. There's also CAS, which is a division of the American Chemical Society, who has put 50,000 antiviral compounds available. And there's, of course, the Sweet Lead library, which has about 7,000 compounds that have been known to be used in humans. So these two together, the targets, the compound libraries, and we're also helping on the computational part. So we have agreements with PRACE, which is the European supercomputer cluster, with GenC, the French one, and we also have private partners that are putting CPU and GPU hours available for the teams that are participating. So after stage 1, we will have a number of lists of all the teams that will cross-correlate to get what we call the ultimate list. So the ultimate list will then, together with Merck, we will screen which compounds can reasonably be made. They will be turned into a physical library of 500 to 1,000 molecules, which we will run affinity assays against recombinant protein targets using our other partners that are in the challenge. And this will give us real binding affinities experimentally determined. And based on that, we will rank the teams, the simulation teams, and award 250,000 euros to the top ranked team. Then in stage 2, we take these molecules with the known binding affinities, and we encourage teams to screen them using live virus assays on cells, and to do that in whatever way they want. But basically, we want to find a compound which has a more than a 2 log reduction of the live virus yields. And on top of that, we want to have at least 100 of these top-ranked compounds from all these ultimate lists to get the data from those compounds. Again, in this stage 2, there's a prize of 250,000 euros. So in the last stage, this is so the first 2 stages are basically a top-down approach where we go from billion compounds, we select 1,000, we screen them, and then we go up. But of course, if we want to have a treatment that is immediately available, repurposing is the way to do it. And of course, many initiatives are already working on this. So the novelty we're trying to bring here is that we are hoping to find compounds that have synergy with each other. And this has been recently developed for HIV. So we hope this approach will also be used for COVID, because it allows us to skip basically the step of one drug, one target that is the most commonly used. So again, we leave it free to teams to determine how they will do that exactly. Teams have to screen at least 1,000 different FDA-approved compounds, and they can do the screening in whatever way they want. But in the end, we are looking for a cocktail which has this more than 2 log reduction of the virus, plus a validation in an animal model. And the top-ranked team here will be awarded up to 1 million euros. So that is our challenge. We are, the official launch is very soon. We were up to now in a pre-launch stage where we were collecting feedback from the scientific community, which we did get. So we're now refining all the metrics. So what you see now is what will go live in a couple of days. So please sign up your teams on our website. There will be also a communication platform to communicate between the teams. And we hope you will all participate. Thank you.
Thank you very much, Thomas. Very exciting. So let's move on and postpone the questions to the joint discussion time, which is after the next 2 talks. So we have another short presentation now by Kostas Kapousanakis about a very interesting new initiative in the UK. I think we already tried to convince them to give a talk in our first ELLIS workshop, but I think Kostas said they just want to make a bit more progress. So we're very happy that this time he's going to tell us about RAMP.
Okay, so am I coming through? Yeah. So RAMP is the Rapid Assistance modeling the pandemic initiative that was convened by the Royal Society in the UK. And the aim was to work with already running COVID-19 initiatives. And we had our target list. There is this scientific pandemic influenza group on modeling that does modeling work on COVID-19 just now. And that feeds into the scientific advisory group on emergencies, and that feeds into the government, the Civil Contingencies Committee of the government. And these are all UK bodies that the Royal Society had access to. And the idea was to put together a RAMP that would fit directly into working groups of SPI-M and also of SAGE. So it looked pretty simple what we were wanting to do. And so what we did was we set up a survey for less than a week. We thought we were going to get about 100 responses or something like that. We got 1,800 responses. And 50% of these are from groups. So it's not like we have 1,800 volunteers. We have a significantly higher number. And quantifying and qualifying what it is we've got is an ongoing, and it seems interminable task, as more people want to join all the time, despite the survey being closed. As I said before, our first target was this SPI-M group, and we did make 70 of our volunteers available to 24 SPI-M groups, and we are also aware of at least one preprint, one output that is directly relevant to the SPI-M groups, and that has been fostered by RAMP. So this is already a good point. The other thing we did, because now obviously we are expanding well beyond the original thinking, we identified a number of pre-existing collaborations that are working on developing fundamental human epidemic models with the aim of adding more resource as they need it, more relevant resource as they need it. Another area which is interesting, and we started going on that, is looking into urban analytics and social modeling. And the idea there is to create new epidemic models that have the social interactions at the forefront and as fundamental part of what it is that they're doing. And what we obviously want to do is to look how human behavior needs to be taken into account when modeling the epidemic. And then something that we always wanted to do is to try and help with the deluge of preprints and publications that are coming out in terms of COVID-19 modeling and intervention. So what we're trying to do is to put together a leadership team and an infrastructure and the processes, of course. So we would allow people to get questions directly from the SPI-M groups and be able to quickly peer review and provide a feedback service to what it is that they're outputting. As I said, we also want to look at what's going out in general. And we also want to see what other people in our community see. So we're trying to crowdsource the procedure of nominating outputs, be they from RAMP or from anywhere actually, and involving the RAMP volunteers to look into these and assess them and then try and figure out what is more worthwhile. So what is it that we're doing now and next? So one of the new topics for us is fluid dynamics of aerosols and how they work with within small buildings and confined spaces and how that would work. And we're trying to add to such initiatives. There is also a new line for us, which is looking at how the virus acts when individuals already carry the infection and trying to understand what happens, the time evolution of this, who are more likely to get it, who are more likely to get it and suffer badly, etc. Another one is we're trying to see what it is that we should be looking at, which would really inform policy making. And we're taking advice from SPI-M and SAGE about this. Obviously, this is very UK-based, what I'm describing here. And the other thing that we're doing is a continuation or an extension, putting together a program for discussion groups and also webinars with invited participants and the participants would be from organizations already running, but also from qualified people who are in the ramp volunteer base. And the idea here is to create live and recorded presentations that would be pedagogic. They would help people get up to scratch with what it is that we're handling here, and perhaps contribute better from that position. And the final thing that I wanted to raise is that we're working with other initiatives in one form or another. And the breadth here is quite wide. So we have DELV, which does inferential modeling of disease. We have DECOVID, which is looking at logistics, etc., to do with how the patients are affected by issues with logistics. ENCORN is operational research. HEC Biosim is molecular modeling. There is also an actuarial response group. UKRI, which is the UK's research councils, effectively are coordinating some R&D work. There's a lot going on, and we're trying to stay on top of that. And with this, I'd like to thank you all for attending this, and especially the organizing committee for giving me the opportunity.
Thank you very much, Kostas. So we are more or less on time. So let's move on with the next talk, and afterwards we'll have a question and discussion session. So next talk is given by Rolf Abweiler, and he will speak about the European COVID-19 research data platform.
Okay, hello everyone. I hope you can hear me. My internet connection was earlier today a bit flaky, so that's good. And let's see whether I can also share the screen. That works. And yeah, can you see it? All good? Okay, good. So yeah, so this will be something completely different. So, but hopefully at some stage quite useful for you. Wait, I need to get, oh yeah, there it is. So the aims of this European COVID-19 data platform we developed together with our Alexia and EOSC Live colleagues at EMBL EBI is to collect European data from diverse sources and of different types to make sure that available research data gets exchanged quickly and shared quickly. We allow for different, sorry, that was the wrong way. We allow for data sets with different degrees of aggregation, validation, and completeness to enter the system. And we hope that this enables synergies and cross-fertilization across the research community. That's, of course, all a bit lofty, and I try to explain it a little bit better. So there are people who do research in the area of COVID-19, that's doing things. And there are people who try to enable research on the service end. That are people like me. And you can see that that we expect various streams of data coming in. One is the SARS-CoV-2 virus biology data. Essentially, it means sequences, RNA sequences. And there is the human COVID-19 biology. That is the host data. There will be, as far as I can see it, a lot of patients will not only get their virus sequenced, but also they get genotyped or exome sequenced or even whole genome sequenced. Because there is the interesting observation that has been already made a while ago that not only old, frail people with underlying health conditions are becoming victim of COVID-19, but also a lot of apparently young and healthy, relatively young and healthy people, where it's unclear why they are vulnerable. And the clue may be in some of a genetic makeup, which through GWAS studies probably could be found out. And that's, of course, pretty important, because if we want to go back to a normal life, we need to find ways to identify the people who are especially vulnerable towards when they get a virus infection, and they need more protection than people who are having no or very mild symptoms. And so, and then there's a whole raft of data generated on the population dynamics of human and the virus. So on the SARS-CoV-2 virus biology, we have set up, and I will talk a little bit more about that later on at EBI, so-called data hubs to deal with that. And the human COVID biology is in the European context, and I think even the global context will be dealt with a federation of the European Genome-Phenome Archive, which can is able to hold this controlled access data in its databases. So that's where we have structures in place. There's also a lot of other research going on, which has already structured homes, mainly at EBI but also at partner databases. And that is in these boxes like protein-protein interactions, phylogeny, and so on mentioned. But the work on population dynamics of human and virus, all of that is really handled by national public health institutes and national infrastructure. It's handled in the research setting, in a clinical setting, and that will not have one central home or not one center of gravitation for such data, but it will be widely distributed and quite dispersed. So, as I mentioned, the virus sequence data will allow us the understanding of the biology, epidemiology, and transmission and evolution of the virus. And for that, we have this COVID-19 data hub set up. The human host sequence and phenotype data allows understanding of the host pathogen interactions, will be dealt with the federated EGA. And the multitude of other research activities, where the European Life Science Research, Bioinformatics Research Infrastructure, ELLIS, is monitoring and cataloging and keeping an overview of the national level activities and data sets to make these relevant sources available for linking into the portal. So that is a rough schematic scheme of it. Patients are entering the national health systems. There are national health data infrastructure, and public health laboratories, which deal with patient information, with virus sequencing, and so on. Some of this can then go into the SARS-CoV-2 data hubs at EBI. This, together with data from other sources which have a structured or not so structured home, these other data sources can then be collected and go into the COVID-19 data portal, and from there this can go to the users. All of that is not done by us in isolation, but in the framework of other European research infrastructures and of the European Open Science Cloud, and there especially EOSC Live. So with SARS-CoV-2 data hubs, they do the sequence data management. So their primary users are really public health agencies and sequencing centers. So we have been in contact so far with 15 different countries in Europe who are interested to use this mechanism to bring their sequences into the public. We have right now the first 2 countries that are putting these data into the private section of their data hub. And hopefully they will be then pushed out very soon into the public. The data we are storing there is really raw data, BAM files, and also then later on the assembled consensus sequences. So all of that will be available later on to the public. So we're expecting already from the ones who told us that we would submit the data, we expect that these 5 countries should contribute something like, at the beginning, something like 1,000 coronavirus sequences a day. And depending on how much they want to ramp it up, it will be, of course, quite a bit more. so that will be a significant significant amount of data. So yeah, that's about this. Host data, human data, where we need to look into an acceleration of a federation of the European Genome Phenome Archive. The European Genome Phenome Archive holds already more than 1 million human genomes. It's in a collaboration right now between EBI and the CRG in Spain. And it's Europe's home for controlled access human genome and phenome data. We had already planned to federate that. Federate means a sort of clone of the EBI CRG instances would be existing in more or less every European country, so that it can get populated with the national data. And therefore would have no troubles with conforming to national legislation, ethical and regulatory restrictions. It would display then the metadata it can display to the whole system, so that people can find the appropriate data sets wherever they are, whether they are in Germany, in Luxembourg, in Spain, in Italy, in Finland, in the UK. So that's now we've had a plan to roll that out essentially over the next 3 to 5 years. I think we're talking here now about 3 months to a year to roll that out in a workable manner. And this is great because it aligns also then with the plans to enable access to national genomic, clinical and phenotypic data collections as part of wider initiatives. And so we'll be just accelerating these developments. It will be not a sort of quick solution just to one problem, but it will be also instrumental later on in the strive towards personalized medicine and genomic medicine in a European-wide setting. Yeah, the COVID-19 data portal would be for the users, the primary entry points. We upload data there, people can find the data there, can download it, they have access to reference data and special tools. We had already for foodborne disease outbreaks pathogen portals and data hubs existing, so we just repurposed some of the code to deal with that. So that was why we could deal with it relatively quickly. So the status of this platform, which consists of these components, hubs and data portal, the data hubs are functional. Data is flowing, and has not made it into the public. But I hope that every day the first country will push the button that it's not only in their controlled space, but out in the public. And then it gets really interesting for people to download it and work on it, not having just hundreds of sequences, but very soon tens to hundreds of thousands of sequences. The COVID-19 data portal was launched on Monday, I have to say. At the moment, it's rather limited. It displays data already in the most important EBI databases and links to the wider Elixir COVID-19 catalog and other resources. I personally would have loved not to release it yet, not to launch it yet, but to wait another 4 weeks before we have to show more and better. So I think, but there was a lot of political pressure to release it very early. Not from EMBL, not from EBI, but from the Commission side, and we understood their concerns and did that. But there's a lot to do. We need to handle all COVID-19 related data sets already in all of the EMBL EBI databases. Not even that we display in the portal right now. There needs to be a lot of user experience-based design improvements. At the moment, the portal is full of jargon abbreviations, which shouldn't be there. They should be understandable for people directly what they are looking at. And I'm not very happy with that, but I say that's straight away here. So we need to do a lot of improvements there. We need to link to the to other relevant European projects and research infrastructures need to link tools or links to tools, and incorporate relevant data sets from other projects. So since this is a constant deployment, we can do all the continuous deployment. We can do quick changes as they come in. So that's good. So I think in 2 to 4 weeks, this will be a really valuable thing. At the moment, I think it's valuable. But as I mentioned before, I would have waited another 2 to 4 weeks with a lot of internal testing and improvements before we made it public. But here we go, it's there, and now we need to do the improvements on the live portal. And with that, I don't want to waste any more of your time, and I'm ready for any questions and say thank you.
Thank you very much, Rolf, and thank you very much all earlier speakers. So now we have a short discussion session. We've collected questions online, and I'm also going to ask into the round of people that are in this call. Also, maybe to get a bit of a lively discussion started, let me ask a question to the first speaker, to Antti. So Antti, you were in one of your slides, you were saying location data is of low utility. So I wanted to challenge that a little bit because one could argue that, for instance, it might make a big difference whether a Bluetooth detected contact happened indoors or outdoors. And it's non-trivial or maybe impossible to detect that just from Bluetooth itself. So you need additional information, and location could give you that information. Or if you wanted to learn about what are hotspots for infection, Bluetooth alone may not be enough for that. What's your view on that?
Possibly, yes. I'm not an expert on Bluetooth signal propagation and its detection. But I mean, that said, I mean, location, I mean, the most problematic cases are indoors, and location, sort of GPS accuracy indoors is pretty low. And also kind of making location data traces anonymous is essentially impossible. So kind of making anything that's based on location data really privacy preserving is basically hopeless.
So it could be useful if it's of high enough accuracy. I mean, for instance, if you have a location data that's not just GPS, but also uses Wi-Fi triangulation, but you're arguing we shouldn't use it for privacy reasons.
Yeah, I mean, of course, I mean, the more precise locations you get, the better, but yes, but I mean, then that would be a privacy nightmare, so.
Okay, so let's move to Thomas. So we have an online question. The question was, what do you consider as the strongest challenge, so the most difficult one for computational methods in this JEDI competition? And maybe I can add, can you just for most of the people here on the call on following in the stream are computational people, machine learning people. It would be good if you say a few sentences about how they could get engaged, where they could get engaged with them. Should they team up with someone else, or do you see a problem that they can solve themselves?
Right. So thanks, Bernard. So I think a big problem is that there are many different computational approaches. I'm not a computational scientist, I'm a chemist, but there are many computational approaches, and people produce lists of compounds like, hey, these are good compounds, let's try them. But the experimentalists are not taking them and actually trying them. So I think we need to improve the accuracy of these methods. And the way we propose to do that in our challenge is by cross-correlating that. And the cross-correlation can be done within a team. So they can take different approaches, maybe deep docking and molecular dynamics and machine learning. Or, I mean, this is outside of my expertise, but hopefully by using multiple approaches and then also cross-correlating all the results of all the teams, we will get the list of compounds that are more reliable. And we have the means to experimentally check. So I think it would be extremely interesting to see from all the computational teams all the different approaches they can come up with, and how we can let's say put them all together and get higher accuracy results. So I just heard that bioRxiv, for example, is now no longer accepting preprints of repurposing predictions only in silico methods. So there seems to be a lot of noise generated in the literature that it's difficult for the other people to take downstream. I think that's a challenge.
Let me ask into the round. Do we have a question of the people who are on the call?
Yeah, I have one here, Bernard. Rolf, thanks for the overview of the COVID resources at EBI. I think one thing that will be very interesting for this audience is, you know, when do you anticipate there to be an interesting data set of a certain scale, and what would it be? Is it mainly the viral genomes that will come first? I mean, there's sort of a question, I guess, you know, where are the opportunities for machine learning and technical scientists to get engaged and prepare for having methods that then can leverage these beautiful data sets that are going to come in the next weeks or months?
Yeah, so I'm pretty sure coronavirus sequences will be a first big batch. For me, it's a bit difficult to estimate exactly when we will get how much, because the final button pushing is depending usually on a lot of internal negotiations between people there on the metadata they send to us. So if it's just the sequence, this is pretty boring. Yeah, it's still helpful, because if you get an idea of the mutation in the space, then you can better plan how you create vaccines, how you try to find intervening drugs. For that, you need to know the sequences, you need to know how to model that onto the structure and so on. That's important. But the real interesting thing for the epidemiologist is, of course, the metadata about, and at the moment, the only minimal thing we ask from people to submit to us is time and location. Yeah, and location can be sometimes as much as the country, yeah, as little as the country. Then we ask for the submission address, yeah, who sent it to us to contact, a number, an ID number, which is usually pseudonymized. Well, it's at least pseudonymized, if not anonymized, yeah. And then, of course, the files, the real data, the raw data, the BAM files, the consensus equals whatever they have. So, and then there are a lot of optional fields. And in some cases, it's allowed to release that, and some cases it's not. And that is depending on the different jurisdictions where the data comes from. So at the moment, there's a lot of, in the background, inside these national systems, there's a lot of discussion, what can we disclose and what we can't disclose. The sequences are much further than the political discussions. And I think that is sometimes hampering the time when they push the final button. So, but having said that, we know that there are that the countries which are involved are all doing thousands a week of coronavirus sequencing, and some are thinking about ramping it up to really tens to hundreds of thousands. So in 2 months, there should be at least tens of thousands sequences out there if it goes all according to plan. Another interesting data set, which will probably come relatively soon, is binding data, chemical binding constants to the proteins where you could interfere with to use as therapeutics. And that are, I think, the first 2 big data sets which will come out and could be of interest.
Thank you very much, Rolf. I would maybe like to have one final question, maybe something for Kostas. We haven't had a question for Kostas yet. Otherwise, I have one. I have a backup question. Kostas, I was intrigued. One of your slides, I think you didn't have time to talk about it. One of your slides, you talked about setting up some kind of rapid peer review. That reminded me of this recent case of this study, the testing study from Stanford, where they estimate the prevalence in the population, asking people to volunteer on Facebook whether they want to be tested, and then they get these very high numbers. And effectively, there has been some kind of Twitter peer review process and heavy debate. So it feels like currently a lot of the things in the publication and maybe also reviewing world are changing, and certain changes are accelerated. So what are your plans with respect to rapid peer review?
Okay, so as I said, we're putting together the processes for this. The initial thinking is that we're going to put together a forum-like structure, and we are already testing one. And we would congregate our volunteers around that. And this structure would allow us to inform them of changes and progress in a much easier fashion than the mailing list we've got just now, which is an announcement mailing list. But this would also foster discussions on specific subjects. So a mode could be, for example, that one of the volunteers identifies an interesting preprint, for example. They put it up on the forum as its own topic, and people get notified of this new artifact, and they comment on it. And what one needs on top of that is a workforce of people who are respected in their areas and who would be able to assess these reviews and understand which of the outputs being judged this way are making inroads towards really addressing COVID, informing SPIEM and the government, etc., and which ones perhaps are not directly relevant or interesting. So as you said, it's a new, we're piloting a new mechanism of crowdsourcing peer reviews effectively, which, you know, it's in the making. It's not something that, as you said, I've not encountered this before. People are used to much more structured reviews of outputs.
Thank you very much, Kostas, and thanks again to all the speakers. So I would like to hand over to the session chair of the last session. It's going to be Michaela van der Schaar. She talked about her own work a couple of weeks ago. And I don't know if we're allowed to say that, but she had some great success. Her tool will be rolled out nationwide in a pilot for ICU capacity planning. So that's very exciting. But without further ado, let me hand over to Michaela. Bye-bye.
Thank you. Thank you, Bernard. So I'm Michaela van der Schaar, and together with Oliver Stegle and Gunnar Raj, I am co-leading the ELLIS Health, which is an important part of the entire ELLIS society and very much related to the discussions we are having in this conference. And it is my pleasure to introduce our first speaker, Victoria Shapakovic. Victoria, are you able to connect?
Yes, I hope yes. And now I will try to share my screen. Yes, should work. Can you see it?
Yes, thank you.
Thank you very much. Thank you very much for introduction. Actually, I'm planning to talk about, I'm a biologist, and I'm planning to talk about device which was developed in our institute, and which allows to detect and to size nanoparticles. So we are using a very well-known physical principle to open the view in absolutely novel world, in the world of nano objects. And certainly any nice analytical device. Oops, it stopped. Okay. Let's try to do it once again.
I think it's just a question of putting them in slideshow again.
Yeah, I'm afraid I will need to close and to open it once again. It's just... Unfortunately, I'm doing it for the first time, and That's exactly the situation when something works when you run it, but doesn't want to work when you so when you try to do it and really need it. Sorry. That's this
Is
one.
your computer frozen?
Looks like, but I think I will manage. Can you see the screen now?
Yes, yes, we can.
You can. So that's good.
But we see it on a wrong slide. At least I'm seeing it on a wrong slide.
Okay. So I think this one. Should work.
Yes, yes, it works
Now it
now.
works.
Wonderful,
Perfect.
yes.
Perfect. Sorry for this inconvenience, and I would like to continue. So I would like to talk about the device which we developed in Leibniz Institute for Analytical Sciences, and this was made together with our colleagues from Technical University of Dortmund, because each and every analytical device, when it's developed from the beginning, requires also development of software which will operate this device and which will help to process and to analyze the data which will be generated by instrument. So in terms of current COVID-19 situation, it is pretty much important to develop a device which will be fast, simple, and reliable, and also, yeah, possibly with a low cost, and which will be able to help us to analyze pooled samples. So imagine the real situation. In airport arrives many planes, and we need to be fast in testing of these people in terms to receive reliable result and during a relatively small period of time. So we don't ask them to wait forever our results and our testing procedure. We also need to use this device, if it is an ideal situation, for testing of environment. So not only testing samples received from human beings, but also drinking water or wastewater, and that may be necessary in the case if we would like to check the environmental situation, or even if we would like to check a situation with food in particular spots in particular conditions. And for that, we would like to introduce our analytical device, which was developed in our institute and based on the principle of surface plasmon resonance. So as you may see over here on this scheme, it is relatively simple, and I will try to explain everything as a biologist. Unfortunately, I am not an engineer or physicist, but I think, yeah, it's a very simple principle. We using just only optical element, which is a glass prism, and if the incidence, this glass prism is covered with a relatively thin nanometer thickness of gold film or film of another normal metal, and if incidence light passes through this prism, it can be reflected from the film and can be detected by a CCD detector by video camera. That's absolutely normal situation, but at a particular angle, the energy of photons becomes the energy of free electron gas which exists in this thin gold film, and no reflection occurs. That's an amazing miracle situation for biologists, because exactly at this point we can understand, okay, we may make a kind of very, very nice sensor, because these reflection conditions, they're very sensitive to any changes near the sensor surface. So if we will immobilize on the sensor surface antibodies, for example, and then particles from the liquid will come and attach to antibody, reflection conditions will change, and again we will be able to see reflected light. That's exactly what you may see on the right panel of the slide. The signal, which we notice, it's a kind of bright spot on the gray background, and this bright spot is bigger than particle. We're detecting nanoparticles, so we're detecting nanoscale objects, but a signal which we have, it's a little bit bigger. It's in micrometer scale because of so-called secondary plasmonic waves. They are actually helping us to detect our objects. And you also may see the other signal which we receive from our detection system. This is so-called step function, when the intensity on the device actually jumps and oscillates on the new level. So as you may see, tests which are currently used for the detection of COVID-19, there are three of them, three types, better to tell. Those which deal with DNA RNA amplification, and mainly this is PCR reaction, polymerase chain reaction, and then also tests based on antibody detection, antibody to viruses. So these tests help to predict immune status of the person who is tested. And they may be very useful for determination of, for answering the question whether a person needs vaccination or not. So these tests are useful not only for current situation, but also for the future. And also our pulmonary sensor may potentially help to detect virus as well as antibody. And as an option, it may also detect DNA of virus, in our case SARS virus, but this is a separate technical story which we also would like to develop.
Julia, in view of time, we have maybe 1-2 more minutes, no more. Sorry, so if you can wrap up.
Yeah, sure, I can. Our current strategy is the strategy to detect particles, and this is the direct strategy when we put antibody on the gold film surface. But we may use also inverted scheme when we put viral antigen on the gold film surface, and we will detect in this case antibody against viral antigen, as you may see. So this will be very helpful, and this is the concept which we are planning to develop and which we are planning to check experimentally in the nearest future. So I also would like to mention what is challenging from the computer science point of view, from the IT cooperative partners who helped us a lot. We recently checked the possibility for our instrument to size nanoparticles which we are analyzing. And as you may see, it's presented in the left part. We used a standard LM10 device from nanoparticle analysis as a reference method. And our pulmonary sensor is at least as good as this method, and that was working using CNNs developed by our cooperative partners in the scope of SFB 876. So I am deeply grateful to all of you for your attention, and certainly to our colleagues from Dortmund, from Professor Morik, Professor Chen, and Dr. Weichert, as well as to my colleagues in ESAS, Dr. Hegenröder, Professor Zickman, and certainly to Dr. Alexander Zibin, who actually developed this device, and I just was taking care about biological part and analysis of biological particles. Thank you very much once again.
Thank you, Victoria. We'll come back with questions. Now let's go for a very short talk of 5 minutes to Plamen Angelov.
Okay, hi. I hope you see my screen or not yet?
Not yet.
Okay. Now?
Stopped. Good.
Can you see it now?
Yes, yes. Thank you so much.
Okay, so I'll be talking about a study that we started and we plan to extend. So we study identification of the SARS coronavirus, and we plan to further this into estimating the severity level of grade and dynamic evolution and prediction. And we use explainable AI. My researcher is Eduardo Suarez. So I'll start with the introduction, data description, and the aims, and go quickly to the approach itself because the time is limited. Concept, the learning phase, validation phase, and the preliminary results. So the study, sorry, is based on real data collected from Sao Paulo Hospital, which are about 2,500 scans, 2,482 scans, split almost equally between people who have and who don't have the virus. And these scans of lungs, you can see them here. The distribution of male and female is almost the same, 32 to 81, 28 with, and equal for no case of coronavirus. This data we made also available in Kaggle, so they are just collected in the last few days or weeks, because unfortunately there are a growing number of data now, as you know. So our aims were to develop a tool which is based on machine learning and artificial intelligence, helping medical doctors make their decision, not only highly accurate, but also to understand and to be able to explain, to understand how the decision was made, to validate this and to allow to continue to learn. This is very important because we are reporting here a study of certain number of cases, but the number is growing all the time. So what do you do? Instead of retraining, the method that we developed can seamlessly adapt to new cases. Also, we try to develop a method which is not compute hungry and data hungry and doesn't use any problem or user specific parameters to tune or to adjust. So it's deep learning already demonstrated some good results in medical imaging, and we extended our approach that was recently published in this archive paper last year. And we use essentially a prototype-based approach, and because of this, we can explain, or we are closer to reasoning. And the key intuition is that we develop prototypes at the points when there is a local peak of the density in the data space. In more specific terms, we develop a layered network, a deep network, and we presented the code here in the GitHub and also published these preliminary results just now on archive as well. So the main, there are a number of kind of procedural steps and equations. The main equation is the density calculated as a Cauchy type of kernel. And the number of prototypes can be visibly traced and can be understood and analyzed. So there are groups of prototypes per class, in this case, just binary, 2 classes. As I said, in the future, we'll go further into several classes when we'll have different degree of the units, but currently it's just SARS or no SARS, or let's say COVID or no COVID. And similarity, which is calculated based on this Cauchy kernel here, indicates, and the winner take all principle is behind the decision. So the results we compared with the benchmark approaches, which are not just decision tree and other boosts, but also several traditional deep learning methods, we achieved a very high kind of F1 score and other performance metrics. 97% in this case. We used 20% for validation of this data. But more importantly, we were able to extract understandable structure or rules, in this case, behind the architecture that we proposed. So we can visualize how and why the decision is made in one way or the other. So here we show the rules for respectively SCAR and SARS and no SARS, and you can see even visually that they are quite different. So medical doctors are more comfortable with this type of transparent approach. So next steps are to enlarge the database, to go to more data as quantity, but also to add parameters like age, sex, previous disease, profession, habits, and try with a fusion of different heterogeneous type of data to build a multi-class classifier and more complex classifier, also to predict the disease evolution. So essentially, I visualize this in this slide, the next 2 type of approaches. So because the time was very short, I was talking a little bit fast, but if there are any questions, we're happy to answer. Just to conclude, again, both the data in Kaggle and the code in GitHub, as well as the paper in archive, are published, and we will welcome any cooperation. Thank you.
Thank you very much. So given the relatively limited time, I wanted to ask whether anybody has any questions. And also I would like to simultaneously open the floor for more general questions and ideas about continuing this forum. How can we take this forum further? Ideas of what discussions we should be having, and how we can best contribute to the general community trying to fight this disease. So I don't know whether there are any questions for any of the 2 speakers, either Victoria or Plamen. So if not, I will ask a question to Victoria myself. So Victoria, what do you see, how do you see machine learning, AI contributing to the research agenda that you have presented?
Actually, I think the main point is to use machine learning at the step when we need to analyze the data which we received. We actually receive very noisy images. You may imagine the situation that we have on the gray background, these bright spots, which may be practically everything. But we need to identify those spots which are our signals. So we need to train neural networks which will recognize those spots as the real signals which can be counted. And further, we need to, after this classification step, we need preliminary classification step, let's say like that. We need to prove that they're real signals, and then we receive the distribution of the signals according to the intensity of the step intensity function, and then we will be able to make a conclusion regarding the size of the particles which we have in our sample. Therefore, we will be able to understand, okay, we have the real information exactly about virus, which currently we know have size around 120, between 120 and 140 nanometers. Current, I think, is 126. And then we will be able to tell, okay, in this sample, we have this concentration of viral particles, and we have a relatively, we're quite sure about this information. So first of all, in the introduction of CNNs in our work, which actually was made previously, and we published, I think, in Census in 2017 or 18, and also recently works describing this application of CNNs in our work.
Okay, thank you so much. So it seems that there is another question for Plamen. And the question is, are you planning to use generative, deep generative models in your research?
It's for me question?
No, no, it's for Plamen Angelov.
Ah, okay.
We cannot hear you, you are on mute.
Sorry, yes, the answer is yes.
Yes. Then we have another question actually for Johannes. And the question is, why don't you put your code on GitHub in a public repository? I don't completely understand the question, but I'm reading it from here. So it is already available. Thank you so much. Thank you. So we would like to thank all the speakers very much for this interesting session today. I'd like to also invite everybody to provide us comments and thoughts about how we can keep this series exciting and informative and enable collaborations among the broader ELLIS community, as well as researchers that engage with ELLIS in all sorts of ways. So if you have further comments or ideas, please send them our way. And if nothing else, no further questions, I'd like to wish you all to stay well and look forward to see you in our next session. Thank you.
Just a brief reminder, next week.
Oh, sorry, Bernard.
So just to remind people, next week is the iClear conference. So the next session is in 2 weeks from now.
Yes, indeed. And if you have nothing better to do on Wednesday, I'm giving a keynote at iClear, so you can listen to some deep learning for medicine. So thank you all. Thank you very much. Bye-bye.
Bye-bye.